Hi, so this is Lab 4 bar magnets, and my name is Ariana. The purpose of this lab was to find the degree of distance dependence of a magnetic field due to a bar magnet, and to find the dipole moment of the said bar magnet, and then to measure and model the magnetic field of a dipole or a bar magnet at various on and off axis observation locations. We used Biot-Savart law as our main physics principle, and the results was that the magnetic field magnitude decreased as distance from the magnet increased. Our exponential distance dependence constant n was calculated as negative 2.985, and our magnetic dipole moment was 2.81. So we use the Biot-Savart law, which is this equation right here for dipoles, where mu is dipole moment, mu naught is a constant, and we can assume that magnetic fields are dependent on the distance from the magnet r to some extent, and that extent is n, where n is a constant and k is also a constant. So our expected value for n based on the Biot-Savart law is -3, because if we isolate the r component of this equation, we get some big constant here, which we represent in our assumption as k, times r to the -3, and thus the expected value for n should be -3. And then these two equations, on axis and perpendicular observation location magnetic field for a dipole, is derived from this large equation, but r hat is either in the same direction as mu or perpendicular to mu. And that's how we get these two equations. And then this image is a visual representation of a bar magnet or a magnetic dipole and the magnetic field around it. So our procedure, we aligned our phone with Earth's magnetic field. We found the magnetometer sensor location and taped it out as shown in this image. And then we found the distance at which there's a specific measured magnetic field. So we moved this bar magnet along a meter stick from far away to close to the sensor until the sensor reading was a specified value, 20, 70, 120, going up by 50 microtesla. So using our initial assumption, b equals k r to the n, we can take the natural log of both sides and find that when graphing the natural log of b versus the natural log of r, the intercept of that graph is going to be ln of k, and the slope of that graph is going to be n. So we did graph it based on our measured magnetic field and distance values, and we found that n was negative 2.985 and ln of k was negative 14.373. So then taking e to the ln of k and basically saying that k r to the n equals our on-axis magnetic field of a dipole equation, because our bar magnet was on the same axis as our phone and oriented parallel, we can divide out r to the n and solve for the dipole moment mu, and we got 2.81. So this is our data and our calculations. And then for the code, we inputted the magnitude of the dipole moment calculated before. And then this function dipole B is essentially just a coded version of the Biot-Savart equation earlier. So the constant mu naught over 4 pi times 1 over r cubed times that 3 dot mu r hat expression. And this function essentially just returns the magnitude of the magnetic field based on a dipole moment and a distance. So then we took 6 observation locations on axis and perpendicular to our magnetic dipole, and we calculated the magnetic field at each of these observation locations and visually represented them with a scaled arrow. The scale factor is here. And then we took our experimental perpendicular distance, which was 0.165, and we calculated the magnetic field 45 degrees off axis of our bar magnet. So this was the result of my glow script model, which you can see here. The magnitude of the on-axis fields, because the bar magnet, the dipole, is this white object. The magnitude of the on-axis field is double that of the perpendicular field, which supports the equations I mentioned earlier. And then some sources of error. There could have been other magnetic fields, there could have been sensor errors, and the phone could have been inconsistently placed, so it wasn't lined up with Earth's magnetic field. There could have also been distance measurement errors. Our results were like I mentioned before, the magnetic field decreases as distance from the magnet increases. our distance dependence constant n was negative 2.985, and our magnetic dipole moment was 2.81. Our experimental calculations validated the physics laws I showed earlier because our distance dependence constant was around negative 3. If we hadn't oriented our experiment to compensate for magnetic north, the Earth's magnetic field would have interfered with the bar magnet's field and skewed both the x and y components of our results. And then if we stuck two identical magnets together, the magnitude of the magnetic field would roughly double, and that's because the value of the constant k would double and the dipole moment magnitude would also double.